So the topic for today is interplanetary trajectories. So interplanetary trajectories in the sense from taking the satellite or taking the spacecraft from one planet's orbit to another planet's orbit. So let us consider for a Mars mission because from Earth to Mars if you want to travel. Okay, for this there's an energy efficient methodology called again interplanetary Hohmann transfer. The same Hohmann transfer for interplanetary trajectories. So that is the first topic of our sixth unit. Hohmann interplanetary Hohmann transfer. And we will see how this is being executed in like in a brief in today's session. Later we will further continue in a little more with some calculations in the upcoming sessions. Let us consider this is your Earth. Let us consider. Okay, so okay, let us say this is your sun. Okay, we'll say okay, we'll say this is sun, and all the planets are anyway revolving around the sun. We know. So let us say this is the uh, Earth orbit that is revolving around the sun, right? So this is let us say this is Earth orbit. Okay, and if we zoom this. Okay, so this is Earth orbit, and there's a satellite. So Earth, this is Earth. Earth is orbiting around the sun, revolving around the sun in this orbit. So this is the orbit of the Earth. Okay, and in the Earth. Okay, so let us say some object. Okay, let us say that is your Earth. Okay, so Earth is revolving around the sun, right? Now I have a satellite or a spacecraft that have been launched from the Earth and it has been revolving around the Earth orbit. So there's, let me say, this is. Okay, so this is the orbit of the satellite. Okay, I'll mention that with a red color. So I have a satellite over here. Okay, that has been launched from the Earth and it is revolving in the Earth orbit. Okay, it is revolving around the Earth orbit like this. Okay, now I have a, what is that? I have a Mars over here. So this is the orbit of the Mars, let me say. Okay, this is the orbit of the Mars, which is also revolving around the Earth, sorry, Sun. And my aim is, so now at some instance, this will come over here. This Earth is also revolving around the Sun. The satellite is revolving around the Earth. Since the spacecraft or the satellite is bounded within the Earth atmosphere, even if you consider Moon also, it will be with a similar orbit only, because it is a natural satellite for the Earth, which is bounded with the Earth gravitational field. So when the Earth comes over here, this ring, this orbit also move accordingly, right? So our aim is this. So this is your spacecraft. Your aim is to take the spacecraft from this orbit to some orbit over here. Let us say like this. Because let me say Mars is over here. Let us say this is Mars. and I want to take my satellite from the Earth orbit to the Mars orbit. It has to be bounded like this in the Mars, let us say. Okay, so how I can perform this? Okay, because unless and until you disturb, this satellite will revolve around this orbit, and it stays like that. And if I so I somehow need to travel or transport it from this orbit to the Mars orbit. Okay, for that is what we call as interplanetary trajectories, interplanetary missions. Okay, so how I can execute this with the Hoffman transfer? Now we know what is Hoffman transfer. It is energy efficient, and few firings, few velocity we need to increase or reduce at some points, and somehow we need to uh, transport like from one orbit to the another orbit. Earlier we have studied. I will now draw this in another way. Now only this red circle. Okay, this Earth. Now I am. This is the real scenario. Whereas now I am taking only this in a separate diagram. Okay, you have to only the Earth I am considering. So let us say this is your Earth. Okay, let us say this is your Earth, which has been bounded under. Okay, some spacecraft has been revolving around the Earth. This is what we have even seen earlier, right? And we said that it was a nearly circular orbit like this. It is not exactly circular, a nearly circular orbit we considered like this. And we said this will be your point A, right? And we said this is your point A. In the perigee, you said that is your point A, and somewhere in the apogee, you said uh, that is your point B, or something. That's it. We can draw. So some point A you have said, and unless and until you disturb, and your aim is to convert from this circular orbit to a bigger outer circular orbit. This was your mission. So to achieve this, what you did is in the previous stage, you gave a uh, you gave a velocity kick in this region, right? You gave a velocity kick over this region and converted from this circular orbit to an elliptical orbit, right? You converted like this. You converted from this circular orbit by giving a velocity kick over here. This circular orbit is being converted to an elliptical orbit, and the spacecraft was revolving like this. Unless and until you give further disturbance at this point. And somehow your aim is to convert to this circular orbit. So at this point B, you gave again a velocity kick, and you have converted from this circular or elliptical orbit to the higher circular orbit. But the thing is, in both orbit 1 and orbit 3, so orbit 2 is the transfer orbit. So in orbit 1 and in orbit 3, in both orbits, the beauty is it is both bounded within the Earth boundary or the Earth gravitational field. So this is where Earth, and in both the cases, so this is where Earth, right? In this both orbits, from the lower Earth orbit to the higher Earth orbit, it is bounded within the Earth boundary or the gravitational field. But when I come here, this is your Earth and this is your Mars. Okay. Your aim is to travel from Earth to Mars. So first, what you are doing is your spacecraft. First, you are sending to space, and it is bounded within the Earth orbit. It is revolving around the Earth. Let us imagine. Okay. So now I am erasing this, and I am bringing out the. This you know already. Okay. This is your. now let me say, so this is your orbit, initial orbit of the Earth, let us say. Okay. So this is not sun, this is Earth. I have just enlarged this diagram. Okay. So this is Earth. And my aim is, so your satellite is revolving somewhere around the Earth like this. Your aim is to take that satellite to another orbit, which is not the Earth orbit. Okay. This is sun's orbit. Okay. So what you are doing is, initially you will give a velocity kick at this point, right? You will give a velocity kick at this point, and you will transfer from this Earth orbit. When you give a higher velocity, it can be taken to a higher elliptical orbit, right? So, this will be taken to an from the circular orbit of the Earth. This will be transformed to an elliptical orbit like this. Okay, and it is very, you will bring the perigee point, you will do the calculations in such a way that the perigee point is very close to the net. One thing you have to very clearly understand here is, still we are not entering into the escape velocity. Okay, once if you're giving the escape velocity 11.6, then of course you cannot control the spacecraft. You don't know where it is going to, it will be out of control of yours. So still you are not going out of the escape velocity. You are not going into escape velocity, but still you are going this orbit. You are taking the perigee very closer to the next Mars orbit. Okay, this is the orbit of the Mars. So now what you will do is, at this point, again you will give a velocity kick. Okay, you are understanding. This is still within the Earth gravitational field, but when it comes to this point, Mars is also there. So this spacecraft will experience gravitational force from both the Earth and from the Mars. Okay, you are getting. And what I will do is, I will further increase or decrease my velocity, so that my aim is to convert this elliptical further into a transfer orbit like this. Okay, I will further convert it to a transfer orbit. Already it is in the from Earth orbit to a transfer orbit, and I will take it to the Mars orbit like this. Again by giving a velocity kick over here. From here I will take it to the Mars orbit, whereas now this spacecraft, it totally will become under the gravitational pull of the Mars, not on the Earth. Okay, so now it can further continue its path in the Mars orbit. Okay, like this. You are getting. So this is how you are doing interplanetary trajectory missions, and you can execute operations from one planet to another planet. And Hoffman transfer is again a two-band transfer. Here it is, one from circular or nearly Earth circular orbit to higher elliptical orbit, and you will take the satellite or the spacecraft to a perigee point, which is very close to the Mars satellite orbit, Mars orbit path, so that at the perigee point of the ellipse, your spacecraft will experience gravity from the Earth as well as little gravity from the Mars also, because it is very close to the Mars orbit. And again at that point, still you can control the satellite from the Earth, because still it is not it is not fully entered into the Mars gravitational field. You will fire again the engine, you will give a thrust again, you will take it further exactly into the transfer orbit, and whereas it enters into the Mars orbit, after that it will further proceed with the gravitation of the Mars. So that will revolve around the Mars. Okay, so in the vice versa, again you have to calculate whether your mission is to come back to Earth, or if you really want to come back to Earth, the same thing in the opposite direction you need to perform. But that is not that easy, because you need to the main drawback you will be facing for a re-entry of these kind of missions, or one is the firing of the engine after a period of time. We don't know how, whether the engine will start or not. Because initially, like for the first 2-3 days, within the first week, you may perform this, you may execute this kind of uh, bands in the engine. But after a period of time, let us say your Mars mission is for some 300 days or something like that. So after that, again, if you want to come back to Earth, you need to again fire the engine, and you need to enter into the transfer orbit again back to the Earth orbit. But when you try to start the engine, it is like a cold crash, because we don't know the climatic conditions over there. It can be very extreme. There are a lot of chances that the fuel that you carry, even if you add some additives, but still there are a lot of chances that the fuel will get freeze or frozen, and there are chances for the engine may not start after a period of time. Even if you try to see your cars and bike, maybe during very cold seasons, morning, there will be a difficulty in starting the engine. So imagine your spacecraft is being happen to be in such a very worse climatic situations. It may have experienced from various positive and negative temperatures. So after a period of time, we don't know whether it will start or not. So that re-entry missions are always very challenging, and very like it is a really a challenging process, and that too particularly when you talk about interplanetary trajectories, because because you are somewhere not within the gravity of the Earth, you are beyond the gravity of the Earth, and taking you back to the gravity of the Earth itself is not that easy, not that easy task to perform. So it needs a lot of calculations and lot of things. But even though whatever calculations you do, there are a lot of chances for the failure of the mission also. So even if you analyze the Chandrayaan also, they have done that only. After a period of time, they just tried of kick-starting the engine, just to say that, just to prove that we have successfully started the engine after a period of time. So what they claimed is maybe the next manned missions when they plan for Moon, even after a week of time, the astronauts do some what is that? Some sort of experimentations or research in the Moon. If they want to start the engine back, only then they can come back to the Earth. So they successfully done it with the Chandrayaan mission, and they proved that even after a certain period of time, they could successfully. They just gave a small thrust. They took the uh, spacecraft to a little altitude, and then again they dropped it down. So that was a testing done by ISRO in the past mission, right? So this is all about the interplanetary Hoffman transfer, and how this is being performed with a two-band impulse, right? So let us stop with this for today, and in the next class we will continue with the uh, next set of things related to interplanetary trajectories. Okay.